Hi, my name is Shamo, a PhD candidate at the National University of Singapore. Thanks for your interest about our recent work, Self-Adaptive Graph Traversal on GPUs. The demand for handling large graphs with low latency motivates the proposal of novel high-performance graph processing solutions, among which exploring the new hardware to accelerate graph processing is a promising direction. In recent years, it arouses wide attention in both academia and industry to explore the GPUs for accelerating graph processing. The advantages of GPU in accelerating graph computation are attributed to its massive number of cores and ultra-high memory bandwidth. However, these advantages do not come for free. The unique hardware design of a GPU brings challenges to efficient programming. The first typical challenge comes from multi-core utilization. As shown in this figure, to accommodate more cores in the GPU, several threads, that is a web, share one program counter. Hence, if they enter different condition branches, for example if-else, then all condition branches can only be executed serially. This phenomenon is web divergence, which will lead to degraded concurrency and multi-core utilization. This makes it difficult to efficiently use hardware resources for application with relatively complicated conditional branches on GPUs. Another typical challenge comes from memory access efficiency. GPU's high device memory bandwidth comes from its relatively long cache line. Its L1 cache is generally 128 bytes, that is 32 single position variables. Data is loaded from memory by cache lines. As shown in this figure, when 32 threads in a web read contains 122 bytes of data concurrently, only one cache line needs to be loaded from the device memory. In this case, the memory access efficiency reaches the highest, that is 100%. However, in practice, this situation is rare. In most cases, only parts of the data loaded at the granularity of cache line is needed. The remaining data is meaningless if it is not accessed before being spread out of the cache. We also note that although the number of cores of the GPU is much larger than that of the CPU, the size of its cache at all levels has not multiplied with the number of cores increasing. This means that the cache allocated to each GPU core is much lower than that of the CPU. Consequently, irregular memory access patterns will be difficult to mitigate by the cache, and the uncorrelated memory access will result in a severe load amplification that degrades the actual memory bandwidth. To adapt GPUs to graph processing application, existing studies propose various dedicated approaches for fully utilizing the hardware resources. Let's look at some examples. The first type of typical technology is based on adding auxiliary structures to change the distribution of graphs by generating a revised replica. For example, we can split nodes with a large odd degree by adding bridge nodes. It is used to elevate the parallel load balancing problem caused by the power law distribution of graphs. Similarly, existing studies also explore to divide the original graph into fixed-size shards and assign the odd degrees with adjacent indexes to the same shard. When performing graph processing, shards are consumed in order. This not only improves load balancing, but also makes concurrent memory access more correlated. Furthermore, the memory access efficiency of graph processing is highly related to the node indexing. Therefore, a series of methods based on reordering has been proposed. They aim to increase the locality of the nodes or degrees so that by relabeling the nodes without changing the topology of the original graph, the memory access efficiency when parallel processors traversing the graph can be improved. Although these approaches manage to improve the performance of GPU accelerated graph processing, they bring some disadvantages at the same time. For one thing, the data rearrangement introduces extra overhead. Some pre-processing techniques are highly time-consuming, which renders a larger starting latency. For another, these dedicated approaches cause a steep learning curve, and thus is not friendly to graph processing developers to migrate their applications to GPUs. Moreover, the requirements of previewing graph application are complicated and evolving. As a result, the high programming difficulty impedes the popularization of GPUs as a graph processing accelerator in practical application scenarios. Motivated by the aforementioned drawbacks, we propose SAGE, a self-adaptive graph traversal, to support efficient graph processing on GPUs. SAGE is free from preprocessing. That is, it starts from the ubiquitous compressed sparse row, that is CSR, as an initial representation. In other words, after loading the graph data in the CSR format on GPUs, SAGE can immediately respond to queries without any launching latency. To achieve this goal, we propose tiled partitioning and resin tile stealing to fully exploit the computing power of GPUs in a runtime and self-adaptive manner. We also propose sampling-based reordering to further optimize the memory efficiency of SAGE through a lightweight and effective node-reordering technique on the fly. To enable SAGE's self-adaptivity, we propose a novel runtime workload reallocation strategy that is tiled partitioning. In particular, the graph data is dynamically partitioned into tiles, the size of which fits the runtime GPU multi-threaded resources. Hence, such tiles are suitable to be consumed by the GPU's cooperative groups of threads concurrently. Let's look at an example. For simplicity, we assume a block consists of 16 threads as shown in this figure. Each of the 16 threads in this block is assigned one frontier, with each frontier's OR degree specified in the grids. Some of the frontiers have large OR degree and are highlighted in bright colors, whereas the rest of the frontiers in gray has only one OR degree. In the beginning, all 16 threads in the block form one tail. Therefore, the large thread and the orange thread will join the election due to their neighbor size being larger than the tail size, that is 16. We assume the red one wins, so that all the 16 threads will cooperatively handle the red thread's neighbors, until the rest of neighbors of the red thread to be handled are less than the tail size. Similarly, the orange thread wins the second election, as there are no other candidate threads, and 16 out of its 27 OR degrees will be consumed. After that, the tail will be partitioned. To be specific, the first 8 threads form one group, and the rest form another group. Then these two groups of threads do not communicate with each other anymore, and each group handles the frontiers with more than 8 neighbors collaboratively within the group. For example, for the first group, yellow and green thread will join the election, and for the second group, it should be these 3. So two groups will handle 8 neighbors within their groups respectively in one step, until all threads do not have neighbors more than the tail size. The task fragments, that is, remaining neighbors of each thread, are no longer considered imbalanced. The approach based on task reallocation to solve the load balance when expanding frontiers is essentially to split a frontier's OR degrees into multiple threaded partitions with specific sizes, and then handle each partition in parallel through adjusting the size of CG dynamically. Though this approach can improve the hardware utilization and parallelism when processing the imbalanced graph data, there still exist several major disadvantages. First, the dynamic adjustment based on real-time leader election in the runtime will introduce synchronization overheads, which restricts the maximum performance. Second, limited by the hardware design of GPUs, such runtime adjustments can only be executed within a block. This means that such adjustments can only function within an SM, but cannot benefit the load imbalance among SMs. Third, such collaborative practice is that the threads are grouped with each thread being assigned several tasks, and then a thread's task will not enter the execution pipeline until the thread wins the leader election in the group. These characteristics will degrade the potential parallelism. As shown, the 16 threads in the tail read the indexes of the OR degrees from CSR, and the whole tail will stall until the end of memory access, generally hundreds of cycles. However, if there is no or not enough other threads of SM waiting to be scheduled, the scheduler has no instructions to emit in the next cycle, and both the compute units and the memory pipeline are wasted. Motivated by the drawbacks of runtime reallocation, we propose to keep the thread arrangement in the GPU's device memory to avoid repeated dynamic scheduling and achieve more effective work stealing. In particular, we adopt a hybrid strategy. That is, when consuming the frontier array and expanding the corresponding OR degrees in a multi-threaded manner, we employ tiled partitioning to split the long OR degree array to tiled partitions with a specific size, as well as suitable to the configuration of the GPU thread group. Further, we keep the online task relocation resource, that is the tiled partitions of a frontier, in the GPU's device memory, as a running context of an auxiliary structure. Hence, when we revisit the all degree of a certain node, there is no need to arrange them dynamically again. In this way, when expanding frontiers, we take two steps. First, we expand the tiled partitions of a frontier resident in the GPU's device memory. Second, CGs consume the tiles with a corresponding size from the tile partition array, and their sizes are adjusted through continuous partitioning until termination. It is clear that, compared with the case shown on the left, this is equivalent to flattening the tiled partitions to process in advance and making them visible to the whole device. Then the aforementioned problems of intergroup load imbalance and memory pipeline not being fully occupied can be solved. Based on the tiled partitioning and the resident tile stealing, the access on the graph data from graph application are concurrent memory access in tiles. However, even for tiles of the same size, the cost of concurrently load them is not equivalent. Let's look at an example. We assume that there are 4 tiles of size 4 that need to be accessed, and a memory sector can store 4 neighbors' values. When tile 1 is accessed concurrently, the required data is in 2 different memory sectors. So although only 4 neighbors are required, 8 neighbors are actually loaded. However, when tile 3 is accessed, data of 3 sectors or 12 neighbors are actually loaded, although only 4 of them are needed. Therefore, the actual memory access cost can be accurately measured as shown in the formula. Based on this, we can reorder the nodes by a bijunction sigma to achieve the optimal memory efficiency, that is, load minimal numbers of memory sectors to access the required data. We have proven that such optimization is NP-hard. Hence, we propose a heuristic approach, that is sampling-based reordering, to derive the formulation. The main idea is that for each node, we try to search a new index for it, which enables the node to have more intra-tile neighbors within the same sector. Let's look at an example. In stage 1, we sample the memory access consists of 4 tiles that read values of the corresponding neighbors in tiles. For instance, when tile 3 is accessed, although only 4 nodes values are needed, 12 nodes values are actually loaded from the memory, since the desired value fall in 3 sectors. Thereby, node 8's locality is 1, meaning that we count the event that one node, that is node 9, within the tile access loads the same sector, in yellow. According to tile access in this stage, for each node, we hereby count the total number of intra-tile neighbors that are in the same memory sector as the locality measure of its index. When the sampled tile access in stage 1 reaches a predefined sampling threshold, we return to stage 2. In this stage, for each node, we try to search a better index so that if the node uses new index, the intra-tile locality can be increased compared with that in stage 1. We look for the potentially better new indexes by binary search. Specifically, starting from the whole interval, for each step of the binary search, we sample and measure which half area has more intra-tile nodes till the searching range converges into one sector. In stage 3, similar to stage 1, we measure the actual locality of the new index obtained in stage 2. In this example, if node 8's index is changed to 3, the locality of node 8 will increase from 1 to 6. According to the locality comparison between 2 indexes is calculated by stage 1 and stage 3, we decide whether to change the index of the current node and update the graph representation. Let's see some evaluation results. We first present the comparison of reordering approaches. The time consumption of each reordering method is shown upon the legend. Particularly, compared with the best baseline, the proposed sampling-based reordering can achieve 95% graph traversal speed in the 5th round with a negligible cost, that is less than 5 seconds, and in the 94th round, Sage catches up with J-order, meaning that sampling-based reordering achieves the same performance at the cost of only less 1% of J-orders. Meanwhile, such cost is introduced gradually, in the runtime rather than a large startup latency caused by preprocessing. Then, we present the comparison of existing GPU-based graph processing platforms. We apply georder to all methods except Sage, since georder performs well for optimizing graph traversal performance. Our proposed Sage exhibits superior performance, especially shows the remarkable performance improvements in social network graphs that are more irregular. This confirms that when processing irregular graph data, tiled partitioning and resident tile stealing in Sage are able to adapt the graph data and the hardware without any preprocessing and fully make use of the GPU's computing power. To validate the impact of our proposed techniques, we apply these technologies, that is, tiled partitioning, resident tile stealing, and sampling-based reordering incrementally to test their influence on the performance. We refer interested audience to the full paper for an extended experimental analysis. To summarize, in this work, we introduce a novel graph traversal approach, Sage, specific to high performance and usability of GPU-accelerated graph processing. We propose tiled partitioning and resident tile stealing to make the graph representation self-adaptive to the hardware and the graph data without the need of any preprocessing. Due to the usage of tile structure, we further optimize the memory efficiency of accessing graph data by sampling-based reordering. Thanks for watching.